Momentum is mass times velocity. You learned it in school. You can calculate it. You can plug it into a formula. You can get the right answer on a test. And every bit of that is fine, except that it has almost nothing to do with what momentum actually is. The thing you were taught is a shadow on the wall. Today I want to show you what's casting it. Let me start where everyone starts. You've got a ball. Let's say it weighs 1 kilogram, and it's moving at 10 meters per second. What's the momentum? 10 kilogram meters per second. Beautiful. You've got a truck. It weighs 5,000 kilograms, and it's crawling along at 2 meters per second. Momentum? 10,000 kilogram meters per second. So the truck has more momentum. Makes sense. It'd be harder to stop. You feel it in your gut. Momentum is how much oomph a moving thing has. Mass times velocity. Done. And look, that's not wrong. Nobody is going to arrest you for saying that. But let me ask you a very plain question. Why should nature care about mass times velocity? Of all the things you could multiply together, why that? You could take mass and multiply it by speed squared. You'd get a perfectly good number with perfectly good units. You could take mass and multiply it by the cube root of the velocity. Why not? What is it about this particular combination of two numbers that makes it so special, that it gets its own name, its own conservation law, its own place in every physics textbook ever printed? If you've never asked that question, you've never really understood momentum, you've just memorized it. So let's go back, way back. Let's find where this idea actually lives. The story most people know goes something like this. Newton wrote down 3 laws of motion. The second law says force equals mass times acceleration. And if you fiddle with that a little bit, you can show that force is really the rate at which momentum changes over time. Force doesn't just push on things, it changes their momentum. So momentum is important, this story goes, because Newton said so. It falls out of his laws. That sounds perfectly reasonable. And it's backwards. Completely, thoroughly backwards. Let me explain why, and this is where things start getting interesting. Newton's laws are wonderful. They describe how objects move when forces act on them. You push a cart, it accelerates. You throw a ball, gravity pulls it into a curve. For 300 years, those laws have been the workhorses of physics. But here's something most people never learn. Newton's laws can be broken. Not in the sense that they're wrong exactly, in the sense that there are situations, real physical situations, where you cannot even define what force means in a useful way. Take 2 electrons flying toward each other. In the old picture you'd say they repel, there's an electric force between them. Fine. But in a more complete treatment, you realize those electrons aren't just pushing on each other instantaneously, they're exchanging photons. Virtual photons, zipping back and forth, mediating the interaction. The force isn't a thing that exists at one moment between 2 particles. It's a whole process, a continuous exchange of messenger particles, and trying to pin down a force at a single instant is like trying to identify the exact moment a conversation becomes an argument. The concept just doesn't cut cleanly anymore. Go deeper into quantum field theory and it gets worse. Particles are created and destroyed. The vacuum itself fluctuates. You try to write down force equals mass times acceleration, and there's nothing stable to attach it to. The force concept dissolves entirely. But momentum is still there. Pristine. Unbroken. Conserved. That should stop your cold. The quantity you thought was derived from Newton's laws turns out to survive when Newton's laws themselves can't even be formulated. So which one is really more fundamental? The law, or the thing that outlives the law? Let me show you what conservation of momentum actually looks like and why it's so much more powerful than any statement about forces. 2 ice skaters standing face to face on a frozen pond. They place their palms together and push off from each other. One glides left, one glides right. Before the push, nobody was moving. Total momentum, 0. After the push, one skater carries momentum to the left, the other carries exactly equal momentum to the right. Add them up, still 0. Momentum is conserved. Well, sure, you say. Newton's third law. Every action has an equal and opposite reaction. That's why it works. And you'd be partly right. But I want you to notice something subtle. Something most people sail right past. I didn't need to know anything about the forces involved. I didn't need to know how hard they pushed, or for how long, or which muscles were engaged, or whether one skater was stronger than the other. I didn't need to measure a single thing about the process of the push. All I needed was a snapshot before and a snapshot after. Total momentum before equals total momentum after. Whatever wild, complicated, unmeasurable stuff happened in the middle is completely irrelevant to the final accounting. That is not just a cute shortcut. That is a profoundly deep statement about the structure of nature. Let me make it more dramatic. Forget ice skaters. Think about a firecracker sitting on a table. It goes off. Bits fly everywhere. 20, 50, 100 fragments shooting out in all directions. Can you track the force on every fragment during the explosion? Can you write down Newton's second law for each tiny piece of shrapnel as the gunpowder burns and the casing shatters? In principle, if you had a supercomputer and perfect measurements of every grain of powder, maybe. In practice, absolutely not. It's pure chaos. Forces are changing every microsecond. Fragments are colliding with each other. Gases are expanding in turbulent swirls. A total mess. But here's what you can do. After everything settles, gather up every fragment. Measure the mass and velocity of each one, being very careful about direction. Add up all the momenta, and the total will be exactly zero. Because the firecracker was sitting still before it exploded, its momentum was zero. And that total is conserved no matter what hellish complexity unfolded during the explosion. Every time. No exceptions. No need to track a single force. Something is protecting this quantity through absolute chaos. It walks through the hurricane untouched. Something deeper than forces at work. Deeper than Newton. This is not just true for firecrackers. Particle physicists rely on this every single day. When protons collide inside an accelerator at nearly the speed of light, they shatter into dozens of new particles. Quarks, gluons, muons, pions, things that didn't exist a billionth of a second earlier. The forces during that collision are among the most extreme in nature. Nobody can write down Newton's second law for that mess. But the total momentum of everything that flies out of the collision equals the total momentum that went in. Always. Every detector at every accelerator on the planet is built on the assumption that momentum is conserved. And it has never, not once, been wrong. And this is not just an academic game. Every medical PET scan that finds a tumor relies on momentum conservation to reconstruct where the radiation came from inside your body. Every calculation that guides a spacecraft to another planet depends on momentum being perfectly conserved during every thruster burn and every gravitational slingshot. If momentum conservation failed by even a tiny fraction, the probe would miss its target by millions of miles. The reason we can trust these technologies with our lives and our missions is that this conservation law holds absolutely in every situation we've ever tested. So what is it? What is the real reason momentum is conserved? This is where the story takes a turn that most physics courses never reach. And honestly, it's a shame because this is the best part. A mathematician named Emmy Noether figured this out in 1918. And what she proved is, in my opinion, one of the most beautiful results in all of physics. It changed the way we understand why anything is conserved. Let me walk you through it, because once you see it, you cannot unsee it. Noether proved a theorem, and the theorem says this: for every continuous symmetry of the laws of physics, there is a corresponding conserved quantity. That's the theorem. One sentence, and it cracks the whole thing open. Symmetry sounds intimidating, but it isn't. A symmetry just means something you can change without anything looking different. Rotate a perfect sphere, it looks the same afterwards. That's a rotational symmetry. Slide a perfectly painted wall to the left by 3 inches. Looks identical. That's a translational symmetry. A symmetry is sameness under change. Sameness when you do something that could have made a difference but didn't. So here is the key question. What symmetry gives us momentum? Translational symmetry in space. The fact that the laws of physics are the same here as they are over there. Sit with that for a moment. If I set up an experiment in this room, get my results, pack up all my equipment, drive 10 miles down the road, unpack everything in a new lab, and do the exact same experiment under the exact same conditions, I get the same result. Of course I do. Why would it be different? The laws of physics don't depend on where you happen to be standing. Space doesn't have a favorite spot. There's no address in the universe where the rules are different, just because of the location. That seems obvious. Almost too obvious to bother saying out loud. And that's exactly why it's so powerful. Noether showed that this obvious fact has an unavoidable mathematical consequence. Because space is the same everywhere, because the laws of physics don't care about your position, there must be a quantity that is conserved in every physical process. And that quantity is momentum. Do you feel the reversal? Momentum is not conserved because Newton told us so. It's not conserved because of action and reaction. Momentum is conserved because the universe looks the same, no matter where you stand in it. The conservation of momentum is a direct consequence of the homogeneity of space. It's woven into the geometry of the world itself. And the same trick works for other conserved quantities. Energy conservation. Where does that come from? Symmetry and time. The laws of physics today are the same as the laws yesterday and the laws a million years from now. That uniformity of time, that temporal symmetry, gives you conservation of energy. What about angular momentum? That comes from rotational symmetry. The laws of physics don't change when you spin around. Face north, face south, face any direction. Same laws. And from that sameness comes the conservation of angular momentum. Every conservation law you've ever heard of has a symmetry hiding behind it. Noether showed us this architecture, and it is the deepest structural insight we have about how the universe operates. And let me flip it around, because the flip is just as illuminating. What would happen if the symmetry broke? What if space were not the same everywhere? Imagine a universe where, for some bizarre reason, the laws of physics worked slightly differently at one particular location. Maybe the force of gravity was a little stronger at a specific spot. Or maybe the rules of electromagnetism had a kink at some coordinate. In that universe, Noether's theorem tells you momentum would not be conserved. An object passing through that region would gain or lose momentum for no apparent reason. It would speed up or slow down without any identifiable force acting on it. Physicists call this sort of thing a violation of translational invariance, and it would show up immediately as a failure of momentum conservation. This is not purely hypothetical, by the way. Inside a crystal, atoms are arranged in a regular lattice. The interior of a crystal is not the same at every point. It has a repeating pattern. Move a tiny amount and you hit an atom. Move a little more and you're between atoms. The translational symmetry is not continuous. It's discrete. And sure enough, the momentum of an electron moving through a crystal is not conserved in the usual way. It gets exchanged with the lattice. The crystal can absorb or supply momentum in specific chunks. Physicists had to invent a modified version of momentum, called crystal momentum, to keep track of things. The symmetry is different, so the conservation law is different. Noether's theorem predicted this perfectly, so there you go. Mystery solved. Momentum is conserved, because space is the same everywhere. Noether proved it. It's symmetry. We can all go home. Except I'm not letting you go home. Because if you think the story ends with symmetry, you're making the same mistake you made with mass times velocity. You've found a deeper answer and gotten comfortable with it. And I just told you 10 minutes ago that comfortable is dangerous. But wait, you say. And I can hear this objection forming. You told me momentum is mass times velocity, and then you told me the real reason it's conserved. Fine, I've upgraded my understanding. What else could there possibly be? I'll tell you what else. Answer me this. Can something with no mass carry momentum? Your instinct says no. Momentum equals mass times velocity. No mass, no momentum. 0 times anything is 0. Case closed. Except the case is very much not closed. Light has momentum. A photon, a single quantum of light, it has exactly 0 mass. Not a tiny mass, not an almost 0 mass. Precisely, definitively, exactly 0 mass. And yet when a photon hits something, it gives it a push. Light exerts pressure. This was predicted by James Clerk Maxwell back in the 1860s when he worked out his theory of electromagnetism. He calculated that a beam of light should exert a small but real pressure on any surface it strikes. And in 1901, a Russian physicist named Pyotr Lebedev actually measured it in a laboratory using delicate mirrors and careful shielding to prove that light pushes on objects. Solar sails are a real engineering concept being developed for spaceflight. You unfurl an enormous reflective sheet in orbit, and sunlight pushes it, slowly, gently, but measurably. That push is momentum being transferred from photons to the sail, collision by collision. How does a massless thing carry momentum? Because the formula you learned is not the real formula. It never was. It's a special case, a damn good approximation for baseballs and trucks and ice skaters, but it falls apart completely for light. The real relationship comes from Einstein's special relativity. For any object or particle, the energy, the momentum, and the mass are connected by a deeper equation. Energy squared equals momentum squared times the speed of light squared, plus mass squared times the speed of light to the 4th power. That is the full picture. Most people have heard of E equals mc squared. That's the famous one. But that equation only applies to objects at rest. It's a special case of this bigger relationship. The full equation includes momentum. When the mass is 0, the equation simplifies beautifully. Energy equals momentum times the speed of light. So for a photon, momentum is simply its energy divided by the speed of light. A photon has energy. Therefore it has momentum. No mass required. Think about what this means. The entire concept of how much oomph something carries never really required mass in the first place. Energy was enough. Mass just happened to be the most visible, most tangible container for energy in our everyday experience. But energy can travel without mass. Light does it all the time. And wherever energy goes, momentum goes with it. The mass times velocity formula was never the whole truth. It was the low-speed, heavy object approximation. And because most of the things we bump into in daily life are slow and heavy, it worked so well for so long that it fooled everyone into thinking momentum was fundamentally about massive objects in motion. It isn't. Momentum belongs to anything that carries energy through space. Mass is just one of the common vehicles for delivering that energy. This is not an exotic footnote. It is essential to the workings of the universe. Stars don't collapse because of photon momentum. Inside a star, gravity is pulling everything inward, trying to crush the whole thing into a point. What resists it? The radiation pouring out of the nuclear furnace in the core, photons streaming outward, smashing into the plasma above them, transferring momentum, pushing outward. The star exists in a tug-of-war between gravity pulling in and radiation pushing out. Without the momentum of massless photons, every star in the sky would cave in on itself. So would the sun. So would we. Laser cooling is another striking example. Physicists slow atoms down to temperatures just barely above absolute zero by bombarding them with precisely tuned laser beams. Each photon that hits an atom and is absorbed transfers a tiny kick of momentum in the opposite direction of the atom's motion. One photon barely makes a difference, but trillions of them, hitting systematically, slow the atom to a crawl. It is like throwing tennis balls at a bowling ball rolling toward you. Each impact is almost nothing, but keep throwing and eventually the bowling ball stops. That technique earned the Nobel Prize, and it depends entirely on the fact that massless photons carry momentum. Let's go one level deeper, into quantum mechanics. And this is where momentum becomes genuinely strange, genuinely unlike anything the textbooks prepared you for. In the quantum world, momentum is not a property a particle simply has. The way a red ball has the property of being red. It's something subtler, something that depends on the relationship between the particle and the act of observing it. You've heard of the Heisenberg uncertainty principle. Most people state it like this: you can't know the position and the velocity of a particle at the same time. But that wording is sloppy. The precise statement involves position and momentum. The more precisely you pin down where a particle is, the less precisely you can know its momentum. And vice versa. Not because your instruments are clumsy or because you accidentally disturbed the particle by looking at it. Because that's how nature actually is at this scale. The particle does not have a definite position and a definite momentum simultaneously. The information is not hiding from you. It genuinely isn't there to be found. Why is the uncertainty principle about momentum specifically and not about, say, mass times velocity? Because, in the mathematical framework of quantum mechanics, momentum plays a very specific structural role. Momentum is the generator of translations in space. What does generator of translations mean? It means that the mathematical operation that shifts a quantum state from here to there, that picks up a wave function and moves it sideways, is built directly out of the momentum operator. Momentum is not just a label, it is the engine of spatial displacement at the quantum level. It is what moves things through space. And notice how this connects right back to Noether. Momentum is the conserved quantity associated with the symmetry of space being uniform. In quantum mechanics, that same symmetry appears as momentum being the generator of translations. The classical insight and the quantum insight are the same deep idea wearing different outfits. A particle with perfectly defined momentum has a wave function that stretches across all of space. It's a perfect, unwavering sinusoidal wave with a definite wavelength. Shorter wavelength means higher momentum. Longer wavelength means lower momentum. This is the de Broglie relation, and it tells you something radical. When you talk about the momentum of an electron, you are not talking about a little ball whizzing along a path. You are talking about the spatial frequency of a wave, how rapidly the quantum phase oscillates from one point in space to the next. That is momentum in its truest, most fundamental form. And that perfect wave, the one with exact momentum, it's everywhere. It's not at any particular location. It has no position. That's the uncertainty principle made visible. Perfect knowledge of momentum means complete ignorance of position. Perfect localization means complete ignorance of momentum. The two are bound together, complementary aspects of the same quantum state, and the whole relationship traces back to the structure of space and the symmetry that Noether identified. Let me give you a vivid way to picture this. Imagine you're standing at the edge of the ocean, watching the waves come in. If the waves are perfectly regular, perfectly uniform, every crest the same height and the same distance from the next, you can measure the wavelength with beautiful precision. But where is the wave? It's everywhere. It stretches to the horizon in both directions. It doesn't have a location. Now imagine a single splash. A rock hits the water and sends out a sharp disturbance. That splash has a very definite position. You can point to it. But what's its wavelength? It's a jumble, a messy burst of many wavelengths mixed together. No clean frequency. The electron does the same thing. Definite momentum means a clean, pure wave extending forever. Definite position means a tight packet of many different momenta scrambled together. You can have one or the other, but not both. And this is not a limitation of technology. It's a feature of the universe. It's baked into the relationship between position and momentum, the same relationship that Noether's symmetry implies. Let me pull this all together. You walked in thinking momentum was a homework formula. What you're walking out with is something else entirely. Momentum is conserved because space is the same everywhere. It survives where Newton's laws dissolve. It belongs to light, which has no mass. It lives in the wavelength of a quantum state. It shows up in the electromagnetic field between two magnets, in the radiation pressure holding up a star, in the vacuum of empty space where there's nothing but field. Two magnets pushing each other apart are not really pushing through nothing. The magnetic field between them carries momentum. The field is a real physical thing, a full participant in the conservation law. If you leave the field out of your accounting, the numbers don't add up. Include it, and they balance perfectly. And that brings me to the thing that really sticks with me. We teach momentum in the first week of the first physics course, first equation on the board. And then we walk away from it. We move on to things that sound harder. But the hard part was always right there in Chapter 1, wearing a disguise so convincing that nobody looked twice. You can get through an entire physics degree computing momentum problems, acing every exam, and never once encounter Noether's theorem, never once ask what momentum means for a photon. You can be expert at using a tool and have no idea why it works. Familiarity is the best camouflage in science. The concepts that feel most settled are usually the ones with the most left to discover. I am curious about something. What is another concept you always assumed was simple until you really thought about it and discovered it wasn't? Sit with that for a while. I think you'll find there are more of them than you expected.